compute the double integral over the region R of the function xy with respect to the area element in the region, where R is the triangular region bounded by the lines x equals 0, y equals 0, and y equals 3 minus x. So here is the sketch of the region. Here's the x-axis, here's the y-axis. The x-axis is the line y equals 0, and the y-axis is the line x equals 0. So that takes care of two of the boundaries, are just the axes. And then the third boundary of our triangle is y equals 3 minus x. So if x is 0, y is 3. And if y is 0, then x is 3. So these are 2 points on the line, y equals 3 minus x. So there's our triangular region. This is the line y equals 3 minus x. Okay, so we want to calculate a double integral over the triangle, the region R, the triangular region of the function xy dA. So we will write this as an iterated integral. So double integral of the same function, but instead of writing dA, we'll write dy dx. And we could also write it in the other order, dx dy. And let's discuss how to set them both up, and then we'll calculate one of them. So here's the region. This is x equals 0. This is y equals 0 down here. And this is the line y equals 3 minus x. So let's look at the first integral. We have dy dx. The inner integral is dy. The outer integral is dx. So we compute the inner integral first, which means that the variable in the outer integral, x, is a constant. So here's the x-axis, and we'll take a random x that'll be a point on this line here, and then the y is going to go from here to here. So the y coordinate at the bottom is 0, and the y coordinate at the top is 3 minus the x coordinate. So the y is going to go from 0 to 3 minus x. And then the x can range from 0 to 3. This number here was 3. So the x goes from 0 to 3. And then let's look at that again in the other order. Let's draw the triangle. So this is x equals 0, y equals 0, y equals 3 minus x. This is 3, this is 3. So the inner integral is dx. That means we're treating y as a constant. So let's pick a y somewhere here between 0 and 3. And then for that fixed y, the x goes like that. So the x goes from 0 until it hits the line. So what's the x coordinate here? Well, if we solve this equation for x, it's x equals 3 minus y, just adding x to both sides and subtracting y from both sides. So for a given y, this x coordinate is 3 minus the y coordinate. And then the y, which we had fixed here, is free to move from 0 to 3. Okay, so either of these iterated integrals can be used to calculate this double integral. And it's pretty easy to see that we'll get the same thing in both cases because of the symmetry in the variables. So let's just look at the first one. We have the outer integral, 0 to 3, with dx. We're going to calculate the inner integral. which is with respect to y. So we need an antiderivative. The x is a constant. Antiderivative of y is y squared over 2. And we have to plug in 0 and 3 minus x. So we plug in 3 minus x, and we get x times 3 minus x squared over 2. And when we plug in 0 for y, we get 0. And now we'll do some algebra here. We have x times 3 minus x squared is 9 minus 6x plus x squared. And then we will distribute the x. So 9x minus 6x squared plus x cubed. And this gives us, as an antiderivative, 9x squared over 2 minus 6x cubed over 3, which we can see is 2x cubed, and then plus x to the 4th over 4. We have to plug in 3 and 0 and subtract. When we plug in 0, we will get 0, so the answer is obtained by plugging in just the 3. 3 squared is 9, so this is 81 over 2, and then 3 cubed is 27 times 2 is 54, and 3 to the 4th is 81, so 81 over 4. So whatever the arithmetic turns out to on here is our answer. We have 81 over 4 minus 27, distributing the 1/2, plus 81 over 8. So we'll write everything in terms of eighths. We have 162 over 8 minus 27 times 8 is, we could do 30 times 8 is 240, and then minus 24, so we get 216 over 8, and then plus 81 over 8. So what are our numbers here? 243 minus 216 over 8, and this is 27 over 8.